how we defined those real numbers. We defined those real numbers as cut. That what are cut? Order pairs of sets like L and U. Okay, we defined cuts as real numbers. All right. So here our U is a dependent set. This set is dependent on the L, and L is a subset of rational number with three properties. One, this is not null set. Our L is not a null set, as well as this is not a rational number also. Maybe it is subset, but it is a proper subset, right? So second one is if P is one of the element in the L and Q is some rational number. Note that P is one of the element means P belongs to L. P belongs to L means P is one of the rational numbers. So we have a rational number in L and we have a rational number in Q itself, and that rational number is less than our P. Then what happens? Q is also one of the element in the L. How to look this? You take you remember how to write a cut for our understanding like this. So we have a P. If you are not getting this, please watch the video number 5.5. Okay, so we have P inside L and there is a rational number Q which is less than the P, so it must be on the left side. So this shows that Q belongs to L. Alright, so this property should be there with the L. I am just recalling what are the properties of the L. And if P is one of the element L, then definitely there should be one more element in L such that our P is less than element than the R. That means there is no greatest element in it. If this is our L, okay, if we have P here, we must have R here. If we have R, we must find one more element greater than R. If we have that element, then one more element, then one more element. There is no end to find greatest element in the L. Okay, so there is no one particular element. So L have no greatest element, okay, in it. There is no greatest element in itself. Alright, so what Rudin do is he will take this L, okay, and he will call themselves as cuts. Why? One, this U set is depending on the L, and one more, if you know L, we can define real number. So L is very much important and L is sufficient enough. So we have a cut here, Rudin calls this L itself a cut, and he denotes not by the L, he will denote it by alpha, beta or gamma. One thing, with every alpha there is one real number, every beta there is one real number, with every gamma there is one real number. So maybe he is using alpha beta for that purpose. If you are not finding where I am talking in the Rudin book, I am talking about the appendix part of the chapter 1, 17th page. This is I'm talking about Indian edition, and third edition. Okay, you take the Indian edition, third edition, there chapter 1 and 17th page. In that appendix theorem, appendix part, he is proving the theorem 1.19, which is about least upper bound property. Okay, least upper bound property of real numbers. So he's talking about those, but I am cutting those step 1, step 2 as one single video. Okay, in this step 1, he defined this thing, what is meant by cut, by using the alpha, beta and all those things. And he also says that the intention of the step 1 is to show that the members of real numbers will be certain subsets of rational numbers. See, these are the subsets of the rational numbers. That are two proper subsets of the rational numbers set with these three properties. These are the subsets of the rational number. But we are representing them, we are representing real numbers by these. Okay, how and all those things we discussed in the previous video. Fine. So that is why I went out of the Rudin book, because this Rudin book step 1 part is not enough to understand how to think this one, the members of the R as certain subsets of the Q. For this you need a little bit extra boost from the video number 5.5. Alright, so in this part he also explains two important properties. Alright, so what are those properties means? One, before that, in this video if I write P, Q, R and such kind of things, those are rational numbers, and if I write alpha, beta, gamma, such kind, so those are cuts. Okay, what are cuts? Cuts are this. Cuts are these things. Okay, cuts are these things. This L itself with these three properties. Fine. I'm not going to define cut once again. Fine. So we have alpha, beta and gamma as cuts, PQR as rational numbers. So if P is a rational number in some cut alpha and Q is a rational number which is not in the alpha, then definitely P less than Q. If you write this diagram, it will definitely gives you very easy approach. Okay, we have P here in the alpha, and if we write Q here, this means Q belongs to alpha, but Q does not belong to alpha, so we cannot write here. And P is not equals to Q. Why? Because Q not belongs to alpha. Alright, so Q is also, P is not also. Only one possibility you can write here. There is no problem. Okay, but this shows that there is no problem at least, but not a proof. Okay, so for that we shall prove it by contradiction method. Let us assume that suppose that our Q is greater than P or P is less than Q. Okay, sorry. Oh, I'm assuming. Sorry. Suppose that our Q is less than P. That means we are taking here. Okay, we are taking here. So our Q is less than P. Suppose this happens. What is the thing? I'm not going to show what happens if P is equal to Q. P is equal to Q is very trivial. Okay. P is equals to Q case is very trivial. You can think. So this leads to contradiction. Very easily you can see. Okay, if P is equal to Q, how can P belongs to alpha, Q not belongs to alpha? That is not possible. Suppose Q less than P. What is the second property of this kind of sets alphas? If there is one more element, if this is our alpha, this is our P, and we know if P belongs to alpha, and if there is a rational number which is less than Q, then Q also belongs to alpha, isn't it? You see, if P is there, P belongs to L, Q belongs to rational number, and Q less than P, then Q belongs to L. This is one of the properties. So this must and should hold, right? So what happens? This implies that our Q belongs to alpha. This is a contradiction. So this is a contradiction to the hypothesis that Q does not belong to alpha. We took Q does not belong to alpha, but we are getting this one. So this is a contradiction. So we cannot get this. So only possibility is P is equal to Q. P is equal to Q is very trivial. So the only possibility we left is P less than Q. Therefore, P less than Q. Okay, please remember this one. At least remember this diagram. If P belongs to Q, and P belongs to alpha, and alpha Q does not belongs to alpha, then it must and should lie outside or the right side, isn't it? So let's go for the second one. Again, second one is also very important. Why I'm telling this? Because I need them in intermediate step. Okay, so second one property, if R is an rational number not belongs to some cut, and R is less than some other rational number, okay, then this other rational number, yes, also does not belong to alpha. Again, this is much easier than the previous one. This is alpha here. We already said if all R does not belongs to alpha, the only possibility it is writing outside. So, and R is greater than yes, therefore it must on the right side. Therefore, it should be here yes. R is greater than yes. So this is also not going to belongs to alpha. Okay. So we shall prove it logically. Suppose our S belongs to alpha. What is the second property? Says that since R is less than X and S belongs to alpha, R must belongs to alpha. This is a contradiction. This is a contradiction to the fact that R belongs to, or does not belongs to alpha. So one more thing, if R not belongs to alpha, all the greatest element does not belongs to alpha. If some element not belongs to alpha, all greatest element does not belongs to alpha. Okay. Now let us come to the step number 2. Okay. Before that, I'm just giving my own kind of explanation. Let S be the set of all possible cuts. Okay, you collect all the sets. Okay, is a cut. What is this means? If you collect all the cuts, what do you mean? Every cut has representation of single real number, isn't it? Indirectly saying that, this is indirectly set of all real numbers. Set of all real numbers. So this is indirectly set of all real numbers. So if we define order for this, that it will somehow serves as order for real number set. I will explain that later how that will serve. Okay, so we are our intention is to find an order for this set. Fine, so we are finding it. So say alpha and beta are two elements of S. Okay, if you want to say alpha is related to beta, alpha is related to beta, that relation is alpha is the proper subset of beta. Pictorially it looks like this. If this is alpha, then this is our beta. Okay, when two alphas are given, they may be equal to each other, may not be equal to each other. May not be equal to each other, may says alpha is a proper subset of beta, or beta is the proper subset of alpha, or they are not at all comparable. That is, alpha and beta are not comparable, at least comparable. That means alpha is not a subset of beta. Along with that, beta is also not a subset of alpha. They're completely whole different. All this possible. Okay. What if these any one of these satisfies? This one or this one or this one. Given you take any two alpha and beta. Okay. Either this is satisfiable or this is satisfiable or this is satisfiable. What if that means? That means first property of the order is satisfied. So how to prove this first property of the order satisfies with this relation? Where is our relation? Yeah, here our relation. Alpha is, if you want to say alpha is related to beta, there should be this relation, that is alpha should be proper. If beta is related to alpha, then beta should be the proper subset. Any one thing should happen, or alpha and beta should be equal to each other, right? So how to prove this? Instead of proving, let's check whether this happens or not. Alright, so we are assuming, or we are taking some hypothesis like this. Say alpha and beta are not equal to each other, and alpha is not the proper subset of beta. Not at all proper subset, not at all subset of beta. Okay, then our expectation is beta should be proper subset of alpha. Otherwise, it will not be an order, because if these two not happens, at least this should happen, right? That means if alpha is not equals to beta, beta not equal, sorry, where alpha is not related to beta, then if our R is order, then beta should be related to R. That means beta should be the proper subset of the alpha, isn't it? So let us take these as hypotheses. So this is our hypothesis. So let us assume beta is also not a subset of alpha. Like this case, let us assume both of them are not comparable. Okay, we have this one, let us assume this one also. What happens then? If beta is not, then there exists one element, say p in beta, such that this p does not belong to alpha, isn't it? If A is not a subset of B, then there exists, say A is not a subset of B, then there exists an element A in A such that A does not belong to B. Like this. There is one element, say this is A, this is B, there is one element in A which is not in A. This is not in A, but it is in A, right? So such kind of things is there. So now we have P does not belongs, sorry, P belongs to alpha such that P does not belongs to alpha. So let us write down what we have. P does not belongs to alpha. This implies P is greater than every element belongs to alpha, right? See, this is alpha and our P lights, you should lights outside. So P should be greater than every element. Alright? Or simply Q is less than P. If q is less than p, this is some arbitrary element. You can take any element. This holds good, right? You can take any element of the alpha, it holds good. So q is less than p, and now we have q less than p. P belongs to beta. This implies q belongs to beta. Second property of the alphas, isn't it? See, sorry. See here. We have beta here, we have p here, and we have q here. So q must belongs to beta. If every element, this says that every element, the q in alpha are in beta. This means alpha is a subset of beta, but this is a contradiction to the hypothesis. Contradiction to the hypothesis. So see, we took two cases, right? We took this case, alpha is not equals to beta, and alpha is not a subset of the beta. Then we assume that beta is not a subset of alpha. Then with that assumption, it shows that this one. Why we took the hypothesis like this? Because we want what happens if alpha is not equals to beta and alpha is not a subset of beta. That is why our hypothesis is this. Alright, our hypothesis is this because we want to check what happens if these two happens. So this is fixed one, but this one is our assumption. But why? Because we know this how to deal with them in the picture. The picture says that this should happen. This should happen, okay? But we don't have logical explanation. So for that we go for contradiction method. We assume what we don't want and checking whether that gives a contradiction. Yes, that gives the contradiction. Alright? Because one of the basic thing was alpha is not a subset of beta, but we are getting alpha is a subset of beta. So our assumption is wrong. Alright? So now what we have, this implies beta is not a subset of alpha is wrong. Wrong assumption. What are the reverses of that? Beta is the subset of alpha. There is a case of equality also, but alpha is not equals to beta. Therefore, only possibility is beta is the proper subset of alpha. This means beta is related to alpha. So now what we have, if alpha is not equals to beta, alpha is not related to beta, then beta will be related to alpha. Also showing this is very easy. Alpha is alpha not equals to beta, beta is not related to alpha. Just change the alpha and beta. There is no big deal. Okay, then alpha will be related to beta. What happens if alpha is not related to beta? Beta is also not related to alpha. Does it implies alpha is equals to beta? Let's check. Okay, we are checking this one now. not related to beta. This implies alpha is not a subset of beta, right? Beta not related. Beta not related to well, not related to alpha. This implies beta is not a subset of alpha. Sorry, not a proper subset of alpha. Sorry, not a proper subset of alpha. Fine. So let us assume the alpha is also not equals to beta. We are assuming what we don't want. Alright, we are assuming this one. But we wanted this to be happen. Or we hope this holds good. Okay. So our assumption is this one. So we are taking alpha is not equals to beta. Now what to do? Now pair with the one of the assumption. Alpha is not related to beta and alpha not belongs to beta. Sorry, alpha is not equals to beta. Alpha is not equals to beta. Alpha is not related to beta. Then beta must be related to alpha. But this is a again contradiction, because one of the hypotheses says that beta should not be related to alpha. Okay, let's pair it with the other one. Beta not related to alpha and alpha is not equals to beta. Again, this will help us to show that alpha is related to beta. This is also contradiction. This is also contradiction. So all these three are holds good. Okay, that means if alpha and beta belongs to S, then one of the following will be true. Either alpha is equals to beta or alpha is related to beta. That means alpha is the proper subset of the beta, or beta is going to related to alpha. Beta is the subset. But what Rudin do, he will again write like this. Alpha, instead of relation, he uses the less than symbol. You see, if you use the relation, there is no problem. R, okay, this is one of the relation, but he denotes this by, Rudin denotes this one by this symbol. Okay, why I will tell. Beta less than alpha, any one of them happens. Alright, since these are all associated with the real numbers, comparison with real numbers, these are all associated with the real number. So we have, say this is our alpha, okay, this is our beta. With the alpha, there is one real number, say x alpha. There is one real number, x beta. With every alpha, if with every cut there is a real number, right? So this will happen. What happens if this shows this? I'm not going to prove it, but this clearly shows that x alpha is less than x beta. I'm talking about real less than. Okay, this value is less than this value. This is, we can get such kind of numbers. So now we are proving order by using the there is an order in the real number set by using the set theory, not using this less than symbol, or not using the negative number. Fine. Then we will associate it with the real number, so the things goes well. And if alpha is a proper subset of beta and beta is the proper subset of alpha, then definitely not alpha, I'll say gamma, then definitely gamma is the proper subset. This is very trivial. I guess you will understand this. Okay, so both the properties of the order satisfied. So our relation, or this one, is an order on yes. We can think about order on R also, because if this happens, this also happens. So this is a set theory proof for this one, kind of proof. Okay, so order on yes. So now we defined order on R. How to say if x alpha is less than x beta? According to our order definition, there must be x alpha related. X alpha is corresponded with the, or related with the some cut, and x b. This is a real number. This is also a real number. Alright. So x beta is also with some cut. X beta is also with some cut, and our x alpha is less than x beta. If you want to say that, then it should have should be like alpha less than beta, or alpha is a proper subset of beta. This is a Rudin symbol. Okay. So this is how we look less than from now on. All right. So in next video, we are going to prove with this order our R as least upper bound property. So this is what we are going to deal in the next